Hello everyone. The topic I'm going to present is fair peer-to-peer content delivery via blockchain. I'm Songling He from NJIT, and this is a joint work with Dr. Yuan Lu, Chang Tang, Guilin Wang, and Chase Qishiwu. Content delivery is very useful for content providers to save bandwidth by dedicating the delivery to deliverers. With the dramatic growth of online traffic consuming, many are employing peer-to-peer data transfer to replace traditionally centralized CDN infrastructure by overcoming its drawbacks and correspondingly bringing the advantages. For example, more robust service availability due to the decentralized architecture, and it can avoid bandwidth over-provision to handle peak demands and correspondingly reduce the service cost. Moreover, the peer-to-peer content delivery is complementary to the increasingly popular decentralized storage network in the sense that the decentralized storage network focuses on the robust storage, while the P2P content delivery can provide a reliable and efficient delivery of this content. The primary challenge in the P2P content delivery is that the system has to promise well-deserved items for all the participants. Because if free riders exist, the honest users may choose to leave, and eventually it's gonna cause the system collapse. Conventionally, the fairness means either each party gets the other's item or neither party does. However, we find that the conventional fairness is insufficient in the P2P content delivery setting. Consider the following scenario. Alice as a deliverer first encrypts the data and then sends to Bob, who aborts after receiving the encrypted content. So at this time point, the conventional fairness still can be guaranteed because both Alice and Bob do not learn each other's data. However, the bandwidth for delivering the encrypted data was wasted. And more seriously, an adversary can perform DOS or DDoS attack to Alice, and this is definitely unacceptable in the system. Now let's use one concrete example of fair exchange protocol, say fair swap, to show the insufficiency of the conventional fairness using in the P2P content delivery setting. Fair swap is used for exchanging digital goods for two parties. At a high level, the protocol executes as follows. The user Alice first sends the encoding of the content X to Bob, where the encoding rate is greater than 1, which means the size of the encoding data is greater than the content itself. Then Bob can perform some preliminary check of the correctness of the encoding data. If it's valid, Bob put the deposit in smart contract. Then Alice can reveal the key so that Bob can decode to get the content. Then if Bob finds that the content is invalid, Bob can complain to the smart contract, which runs the pre-deployed judge functionality to resolve the dispute. If the content is indeed correct or after timeout, then Alice gets the payment. Otherwise, Bob gets refund. So in this protocol, in the first step, if Bob maliciously aborts after receiving the encoding data of the content, then all the bandwidth resources that Alice used to send the encoding data are wasted. To mitigate such an issue, one straightforward solution is to split the content into multiple chunks, then execute the fair swap protocol of each chunk between Alice and Bob. But in that case, the on-chain cost will become linear with the number of content chunks. So it is obvious that using this kind of fair exchange protocols is not suitable in the P2P content delivery setting. The core reason is that the conventional fairness is used to guarantee the exchange between digital goods, but for the specific content delivery setting, the contribution made by Alice as a deliverer is bandwidth, which can be thought as a kind of service instead of digital goods. To this end, we need more fine-grained fairness in the sense that we define conventional fairness as exchange fairness, while for the deliverer we propose and highlight that the delivery fairness should be guaranteed in the specific P2P content delivery setting. That is, the deliverer should be able to prove to others about the bandwidth contribution and get proportional payment. Besides the observation that existing fair exchange protocols are not suitable in the P2P content delivery setting to guarantee the fairness, we also notice that existing works that are related to the content delivery implicitly present the guarantee of delivery fairness that we define in our paper. However, these works consider the non-cooperative game theoretical model. in which the attacker free ride spontaneously without negotiating their attacking strategies. Also, the attackers are rational in the sense of intending to maximize their own benefits, and the design of these protocols may not be secure. For example, a competitor may exploit the insecure part of the protocol to perform the attack, even though they may not obtain the benefits in a short time period. So the security of these protocols are not proved in the cryptographic sense as we seek to do in our paper. So not only the delivery fairness for the deliverers, the exchange fairness for the consumers and the providers should also be guaranteed, where the providers should receive the payment proportional to the amount of correct data learned by the consumer. And for the consumers, they only need to pay if indeed receiving the qualified content. But a naive or maybe straightforward way to apply fair exchange protocols twice between the provider and the deliverer, and also between the deliverer and the consumer, does not work. First, it's gonna leak the content to the deliverer, who should not be able to see the content during delivery because the target user is the consumer. Also, it is not compatible with the general content delivery paradigm, because such a straightforward way requires the deliverers to pay before making a live by delivering content. And meanwhile, in the general content delivery paradigm, consumers who want to buy the content should pay for the provider instead of for the deliverers. So it also remains challenging to guarantee the exchange fairness in the P2P content delivery setting where three parties are involved. And more discussions about the non-applicability of existing method to the specific P2P content delivery setting are presented in our paper. With this fine-grained fairness, now we can formalize the P2P content delivery, where the designed protocol can guarantee the fairness for each party, even others are corrupted or clued. It is well known that a fair exchange protocol cannot be designed to provide complete exchange fairness without a trusted third party. Here in our protocol, we leverage blockchain to play such a role to assist content delivery and help guarantee the fairness. Specifically, we require the fairness for each party as follows. For the deliverer, it is paid nearly proportional to the bandwidth contribution. For the provider, it is paid nearly proportional to the content that is earned by the consumer. While for the consumer, the payment by the consumer is proportional to the correct content that he or she earns. Here, the correct means we consider a globally known predicate that can be used to check the correctness of the content, for example, the Merkle tree root in our protocol. Besides fairness, we require other necessary properties. Here, completeness means at the end of the protocol, all honest parties get the desired output. Where the provider gets the payment for providing the content, the consumer obtains the correct content. The deliverer, by contributing the bandwidth, can get the payment from the provider. Essentially, the provider receives a net income, that is, the payment received from the consumer minus the amount paid to the deliverer. The property of confidentiality against corrupted deliverer means the deliverer cannot produce the provider's input content in a protocol instance. That is because if the deliverer can get the plain text of a content in a delivery session, any consumer then can pretend to be the deliverer or collude with the deliverer to get the content without paying for the provider. The property of timeliness requires that the protocol terminates in ON rounds, where the N is the number of the chunks of the content. Also, at completion or abortion of the protocol, the properties of fairness and confidentiality are always guaranteed. Besides the mentioned security properties, the protocol also requires the following non-trivial efficiency. First, the messages sent to the contract is bounded by O-1 bits. This rules out the trivial solution by letting the smart contract directly relay the content to consumers. Second, we require that in the delivery, the messages sent by the provider should be much less than the content itself, since otherwise the provider can deliver by herself, which is obviously not the purpose of using P2P content delivery. In this paper, we proposed two P2P content delivery protocols that cater for two settings, downloading and streaming. At a high level, first, the content is split into n chunks, and the validity check of the content is a public knowledge to all parties. In the downloading setting, the provider starts the protocol by deploying the smart contract and put deposits, which is going to be paid for the deliverers. Once delivers join in, the provider can select and delegate encrypted and signed chunks to the delivers. Now, if a consumer joins in by putting the deposit, then the deliverer can start to deliver all the chunks and then get the payment from the smart contract. Then the provider can reveal the chunk decryption keys on chain using which the consumer can decrypt the chunks. If invalid chunk is found, the consumer can provide proof of misbehavior to the blockchain to get a refund. Otherwise, the provider gets the payment after timeout. In the streaming setting, the first two steps are the same. First, the provider starts the protocol by deploying the smart contract and putting deposit. Then once the deliverer joins in, the provider can delegate the signed and encrypted content chunks to the deliverer. And now the deliverer is ready to stream the content. So once a consumer joins in by putting the deposit in the smart contract, the deliverer starts to stream. The key difference with the downloading setting is that the consumer can get an encrypted chunk and also a decryption key in the same round, instead of waiting for all the chunks to be downloaded. Then if the consumer finds invalid chunk, the consumer can immediately complain to the smart contract. So the consumer can get compensation if the chunk is indeed invalid. One remark here is that in the downloading setting, the consumer can get a refund of all its deposit if indeed received the incorrect chunk. But for the streaming setting, the consumer needs to pay for the successfully streamed valid chunks. So it cannot get the whole deposit back. In that case, for both downloading and streaming protocols, the provider is required to put some deposit as penalty fee to discourage his misbehavior. And this penalty fee is proportional to the whole content price so that the provider cannot deliberately lower it. Later, the provider and the deliverer can claim the payment from the smart contract. Now I'm going to present the key design thoughts in the downloading protocol. First, we have a building block called verifiable fair delivery, which can be used to prove and quantify the bandwidth contribution for the deliverer, which is the sender here. The idea is the content is split into n chunks, each is of size eta bits. The sender sends the chunk 1 to the receiver and waits for the signature. Only if the signature is valid, the chunk 2 is gonna be sent out. Such a mechanism that looks very simple has several advantages. First, it can quantify the bandwidth contribution using the latest signature. Second, at most, the deliverer loses the bandwidth of delivering one chunk of size eta, so the unfairness can be bounded by the system parameter of the content chunk size. Last but not least, it's very efficient, which is very important to the content delivery setting. With the verifiable fair delivery building block, the protocol of fair peer-to-peer downloading works at a high level in 4 phases. In the prepare phase, the provider starts the protocol by deploying the smart contract and initialize the necessary parameters. Here, H is the marker root of the content X, N is the number of content chunks, $C is the price for each chunk of selling to the consumer, and $P is the price for each chunk delivery that the provider is gonna pay for the deliverer. Locally, the provider uses the N chunks to build the marker tree of the content. Now different deliverers who are interested in delivering this content can join in. Then on the provider's side, for the N content chunks, the provider can generate a key tree, where the MK is a master key that is randomly sampled. Then the N leaf nodes of the key tree can be used as the encryption key to encrypt the N content chunks. These encrypted content chunks will also be signed by the provider and generate a sequence of pairs. This sequence of the encrypted chunks and the signatures are then delegated to the selected deliverers. This process is off-chain. Once the deliverer received all the encrypted chunks and verified the signature, then the deliverer can send the prepared message to the smart contract, which is gonna mark the contract status as ready. So at the end of this phase, for the provider, it holds the marker tree of the content X and also it holds the key tree with the master key MK. While for the deliverer, it holds the sequence of all the dedicated content chunks and the signatures. And now the deliverer is ready to deliver the content. Now in the deliver phase, a consumer who is interested in the content with the identifier H can send the consume message to the smart contract. With this request, on the one hand, the provider shows up to send the marker tree and the signature of the marker tree to the consumer off-chain. On the other hand, the deliverer and the consumer invoke the fair delivery module. where the deliverer acts as the sender and the consumer acts as the receiver. At the end of the execution of the module, the sequence of the encrypted chunks and the signatures are delivered to the consumer. And correspondingly, the deliverer receives the signature from the consumers as the proof, which can be used by the deliverer to prove the bandwidth contribution. Assume the number of delivered chunks is denoted by CTR, where CTR is less or equal to n. Then the deliverer can use the latest signature and send to the smart contract, which would verify the signature and send the corresponding payment to the deliverer. As analyzed in the verifiable delivery module, if the number of delivered chunks is denoted by CTR, then at least the deliverer can receive CTR-1 signatures. So intuitively, at most, the bandwidth resource of delivering one chunk of size eta may be wasted. Then in the reveal phase, based on the value of the CTR on chain, which represents how many chunks have been delivered, for example, for the 7 keys, 3 elements in the key tree need to be revealed. Then in the best case, only 1 element needs to be revealed, and in the worst case, log n elements may need to be revealed. These revealed elements marked by the blue color are later revealed on-chain. So essentially, the storage cost of these elements on-chain is O_1, which means in the worst case it's log n, where n is the number of content chunks. So after computation, the provider is going to use the public key of the consumer to encrypt these elements and revealed on-chain. Then in the next step, the consumer can use his secret key to decrypt this revealed element and then recover CTR keys in the key tree, because the key tree is deterministically generated. So essentially, the recovered keys are those that the provider used to encrypt the content chunks. Then the consumer can use these keys to decrypt the received chunks to get the raw content chunks. For each content chunk, the consumer is going to compute the hash value of it, then compare each of them with the leaf nodes of the Merkle tree that received in the previous phase. If there is any chunk that is inconsistent, the consumer can raise complaint to the smart contract. In the dispute resolution phase, the consumer can send this information to the smart contract as the complaint, where I is the index of the invalid chunk, J is the index of the revealed elements in the key tree that can induce the ith invalid chunk. Ci and the sigma CIP is the encrypted chunk and its signature received in the deliver phase. HXI is the ith leaf node in the Merkle tree that bonds to the Merkle root H on chain, and PyMT is the corresponding Merkle proof. For the other 3 data, RK, ERK, and PyVD, first, ERK is the encrypted revealed element of index J, which can be decrypted to RK with the proof PyVD showing that indeed ERK is decrypted to RK. With this information at a high level, the smart contract can verify the misbehavior as follows. First, the ith encrypted chunk is indeed signed by the provider. Second, the encrypted revealed element on-chain is also from the provider, and we have a proof that can verify the ERK indeed decrypts to RK. With the RK, which has the index of J in the key tree, and the smart contract also knows the index of I, then the smart contract can compute a unique path from J to I. With this path, the smart contract can use RK to deterministically generate Ki, and then use Ki to decrypt the corresponding encrypted chunk to get the raw chunk, then can compute the hash value of it, and compare with the value in the Merkle tree that bonds to the identifier H. If equals, it means the provider does not provide invalid chunk and the consumer complains failed, or else the consumer successfully complained and would get a refund. Besides the verifiable fair delivery module to quantify the bandwidth contribution, we also want to highlight other 2 main designs in the fair download protocol. First, definitely the storage cost will be huge if we reveal all the chunk decryption keys on-chain. To minimize that, we proposed the structured key derivation scheme, which contains 3 algorithms. The generate subkey function can take a randomly sampled master key and deterministically generate n keys for chunk encryption. Then during revealing, according to how many keys need to be revealed, in the best case, only one element is revealed on-chain, and in the worst case, the revealed number of elements is O log n. Overall, it is O tilde 1 of the on-chain storage cost. Later, the revealed element is used to recover all the keys for chunk decryption. Second, we dedicatedly construct efficient verifiable decryption based on standard cryptographic primitives. Specifically, we use algorithm encryption to encrypt the revealed elements from the provider and reveal on-chain, in which the revealed elements are encoded using Koblitz method. We adopt Schnorr protocol for Diffie-Hellman tuples using Feld-Shamir transform in the random oracle model. And we will see the concrete on-chain cost in later experiment part. Now I'm going to briefly analyze the fair download protocol satisfies the design goals. The completeness property is very obvious to see, so if all the parties are honest and follow the protocol, at the end of the execution, the consumer gets the qualified content and pay for it. The deliverer gets the payment for delivering the n chunks, and for the provider it gets the payment of the net income. That is, it pays for the dedicated delivery to the deliverer, while receives the payment from the consumer for providing the content. For the fairness property, the consumer pays for error chunks only if it receives error-valid consecutive chunks of the content. This is because if any invalid chunk is found, the consumer can always complain to the smart contract and get a refund. For the deliverer, if it sent error-dedicated chunks to the consumer, at least it can receive the payment for delivering error-1 chunks, and this is guaranteed by the verifiable fair delivery module. For the provider, if error chunks of the content have been leaked, then the provider would receive the net income of error chunks. This is because as soon as the deliverer claims the payment from the smart contract, the number of delivered chunks will be recorded on-chain. So unless the execution of the smart contract can be controlled, or the consumer can come up with an illegal but valid proof of misbehavior so that led the smart contract to repudiate the payment to the provider. But realizing this means breaking the security of the underlying primitives, so the fairness can be guaranteed. For the confidentiality against corrupted deliverer, it is obvious that in a protocol instance, the corrupted deliverer cannot produce the provider's raw input, because all the dedicated content chunks are encrypted, and also the revealed key on-chain is also encrypted using the consumer's public key. For the timeliness property, the fair download protocol terminates in ON rounds. This is because in the deliver phase, the content is delivered chunk by chunk, and the rounds in other phases are constant, so overall it is ON rounds. Also importantly, at completion or abortion of the protocols, the fairness and confidentiality are always guaranteed. And the guarantee of these properties aborting each step is analyzed in our paper. For the efficiency property, the messages sent to smart contract are uniformly bounded by O tilde 1 bits. The messages are mainly from two parts. In the reveal phase, the revealed elements submit to chain in the worst case is log n. And if dispute happens, in the dispute resolution phase, the Merkle proof in the complaint submitted to the smart contract is log n. And in other phases, the messages sent to contract are of 1. So overall, these messages can be denoted by O tilde 1 bits. Meanwhile, consider the content has been dedicated to the deliverer. The messages sent by the provider is much less than the content itself. So in the downloading setting, the provider needs to show up twice. The first one is for sending the Merkle tree, and the second is for revealing the at most log n elements on chain. So overall, these messages are much less than the content itself. Aforementioned are the protocol design for the downloading setting. Besides downloading, the content streaming is also a very common scenario. However, the verifiable fair delivery module designed for the downloading setting is no longer suitable for the streaming setting, because the delivered items are encrypted content chunks. While in the streaming scenario, each content chunk should be retrieved in OI rounds instead of waiting for all the chunks to be downloaded. To that end, we proposed the second P2P content delivery protocol, Fair Stream, that is suitable for the streaming setting. At a high level, the streaming protocol operates in 3 phases. The prepare phase is the same as the downloading setting, so the provider dedicates the encrypted and signed chunks to the deliverer. Then in the stream phase, once the consumer joins in and put the deposit in smart contract, The deliverer starts to deliver the content by sending the chunk. Now the consumer does not immediately send back the receipt. Instead, the consumer sends a request of the key to the provider, and then use the key to decrypt the received chunk. The consumer can validate the chunk and decide whether to raise complaint. If the chunk is valid, the consumer sends back the receipt to the provider and the deliverer respectively. The deliverer will verify this signature and decide to send the next chunk or not. And similarly, the provider will verify the signature and decide whether to send the next chunk key upon receiving the consumer's request. So in this maybe simple but efficient way, we realize the streaming of all the chunk delivery. And at the end of this phase for the provider, it receives a set of signatures from the consumer, and the same for the deliverer. Note that in the worst case, the provider may lose one chunk, and the deliverer may also lose the bandwidth resource for delivering one chunk. But again, at most one chunk, so the unfairness for the provider and the deliverer can be bounded. Also, during streaming, if an invalid chunk is found, the consumer can complain to the smart contract by sending such a message. So with this information, the high-level idea of how the smart contract can verify the misbehavior is as follows. First, the chunk is signed by the provider, and then the key is also signed by the provider. So the smart contract can verify these signatures and then decrypt to get the raw content chunk. Then similar to the downloading setting, it's gonna hash the content chunk and compare with the corresponding leaf node in the Merkle tree. If false is returned, it means the consumer successfully complained and will get the compensation. Otherwise, it goes to the next payout phase. In this phase, the provider and the deliverer sends the latest signature that received from the consumer to the smart contract, which decides the final number of delivered chunks as the maximum index of what the provider and the deliverer submit. Here, using the maximum number of what the provider and the deliverer submit can help ensure the fairness and prevent the case that either the provider or the deliverer maliciously lower the final counter. We omit the security and the efficiency sketch for the fair stream protocol here, but the key difference with the downloading setting is that for the provider it may lose one chunk without being paid, but this is covered in our security definition. And for both fair download and fair stream, they realized the same security and efficiency goals. Now I'm gonna show the experimental results for both protocols. We implemented, deployed, and evaluated the protocols on Ethereum Ropsten network. The table shows the on-chain cost of all functions in the downloading setting. Figure 1 shows that in the optimistic case where no dispute happens, the overall on-chain cost is constant, while in the pessimistic case, the overall on-chain cost depends on the chunk size. Figure 2 shows the on-chain storage cost of all the revealed elements in the worst case. In the streaming setting, we streamed 512 chunks of various size in both LAN and WAN. Figure 4 and 5 show that the average latency of the streaming. And we can see that the streaming is stable and the time cost obviously increased due to the chunk size. Correspondingly, Figure 6 illustrates the average time cost for each chunk and the corresponding bitrate. The result shows that the bitrate can reach about 10 megabits per second even in the public network, while a typical HD video bitrate is about 4 to 8 megabits per second. In that sense, our protocol can in principle support high-quality content streaming in a fair way. And the left side table shows that the on-chain cost of all the functions in the streaming setting. And we highlight that for both downloading and streaming setting, our protocol supports repeatable delivery so that the one-time deployment cost can be amortized. Some takeaway messages from our protocol design are that, first, verifiable fair delivery module is used to quantify and prove the deliverer's bandwidth contribution. Second, a structured key derivation scheme is proposed to facilitate chunk delivery and reduce the on-chain cost to OT at 1. Also, efficient construction of verifiable decryption can further improve the on-chain verification of proof of misbehavior from the content provider. Some future works and extensions are: a mechanism is needed to adaptively select a deliverer for maximize the delivery performance. Also, a dynamic deposits adjustment scheme can help decide how much of the deposits that the providers and consumers need to put in the smart contract. Furthermore, to preserve the digital rights of the sold content against pirating consumers, It is possible to use, for example, digital rights management schemes. Of course, there are still many issues to explore in the P2P content delivery topic. We will keep digging into this field, and we encourage and welcome other researchers to join in and discuss more about this topic. Thanks for watching this presentation.